In this lecture, we will continue talking about basic ideas of ODEs that are going to be applicable throughout this course. And in particular, I want to expand upon the issue that we discussed last time. So if you have an nth order differential equation that I have written here in the normal form, remember that the normal form is when you write your ODE expressed as an nth derivative, as a highest derivative equal to a function of lower derivatives. So if we have an nth order ODE like this, then we discussed that in order to produce a solution of this ODE, I have to get rid of the nth derivative formally. And I can get rid of the nth derivative by integrating n times. And when I integrate n times, then I should end up with n unknown constants. And therefore, a solution of this equation should be an expression that involves an unknown or generic constant. And we term that an n-parameter family of solutions. So a guy like this will have an n-parameter family of solutions. We said that any solution which does not involve any parameters we're going to call a particular solution. And so in order for us to find a particular solution of this equation, in addition to the equation itself, I'll have to specify n additional conditions that will allow me to determine these n parameters. So what we're going to do, we're going to fix some initial value of x that I'm going to call x0. And at this point, x0, we can then specify a bunch of information about function y. And we need, like I said, n conditions. So one systematic way in which you can specify n conditions will be this. You prescribe the value of the function at the point x0. It gives you one condition. Then, in addition to that, you can prescribe the slope of y at x0, and let's call it y1. That's two conditions. And if I can keep going like this, I can prescribe the second derivative, third derivative, and so on, up until I hit the n minus first derivative. And I can specify that as well by setting this to be some number yn minus 1. So these numbers from y0 to yn minus 1 have to be specified as conditions of my problem. All right, so then what do I see here? I start from a function itself, which I can think of as a zero of derivative. So you start from a zero of derivative, you end up with n minus first derivative. So if you count from 0 to n minus 1, that's going to be exactly n conditions. So then in order to find a particular solution, I need to specify my nth order equation and n initial conditions like this. And therefore, I should be able to find a single particular solution by solving a problem like this, which consists of a differential equation and initial conditions. And I already previously mentioned that an object like this is called an initial value problem. So that's one of the main things that you want to do when you're solving ODEs, is to solve initial value problems. Because as we'll see from the next couple of examples, in physics and geometry, that's sort of a thing that you'll see arising, initial value problems. One thing that I'm not going to expand upon at this point is that it's not necessarily, nobody says that you have to specify n conditions at one point. You might specify conditions at different points. For example, and we'll see that that will lead us eventually at some point in the future to something called boundary value problems. But we're not going to worry about that right now. All right, so let me give you a couple of examples. One you have already seen in the first lecture. So remember that in the first lecture, I considered an example of a ball that was dropped to the ground from some initial height x0 from the position of rest. So you just hold the ball at the height x0 above the ground, and you simply release it, and it falls to the ground under the action of gravity. And I wanted to find the position of the ball at any moment of time. So if remember, we denote by x of t the height or the altitude of the ball above the ground. Then x is a function of t. Then x prime of t will give the velocity of the ball. So in this case, if the axis x of t was pointing up and the ball is falling to the ground, then x prime must be some sort of a negative number at all values of t. And then x double prime of t is going to be acceleration. So again, if ball falls to the ground, and in this case, again, I'm assuming absence of air resistance. So then it only falls under the action of gravity force. Nothing resists the gravity force in this case at all. So that means that velocity is negative and always increasing. So x double prime of t must be a negative number as well. And indeed, what we know is that from the second Newton's law, mass times acceleration is equal to the gravity. So in principle, I should have had here mass times x double prime is equal to minus mg, but then m cancels out. So we just have that acceleration of the ball is equal to minus gravitational acceleration. We know the initial condition, initial height of the ball, initial position. And we know initial velocity because the ball was dropped from rest. So initial velocity is 0. And so then what you need to solve is a combination of a second order ODE and two initial conditions. So this is a second order initial value problem. And we did solve it in the example in the first lecture simply by integrating with respect to t. So integrating the equation with respect to t, but I'm not going to repeat it here. Just to motivate that for this physics problem, you need to solve a second order initial value problem. Another example I'm going to borrow from geometry. So here I'm going to make the following assumption. I'm going to assume that I have a family of curves on the plane. So maybe entire plane is covered by curves. And let's say the information that I have is this. Somehow I know that when a curve passes through the point xy and on xy plane, through any point xy on xy plane, somehow I know from some source, I don't know, doesn't matter how, I know that the slope of the curve must be equal to y over x. And what I want to do, I want to construct one of curves from this family, starting from some point x0, y0. Okay, now let's reformulate this in a mathematical language. My first statement is that the slope at any point is equal to y over x. So that means that whenever whenever curve passes through the point y over x, then the slope at that point is equal to y over x. So what is slope? Slope is y prime. So that means that the curve must satisfy this ODE that is circled on the screen, that y prime is equal to y over x at any point xy. That's number one. And number two, I want the curve to pass through the point x0, y0. So that means that the value of y at x0 must be equal to y0. And I see that I have my ODE, I have the initial condition. So overall, this is an initial value problem of the first order. Let's do an example of this. So a more specific example of this. So rather than looking at a generic x0, y0, let's suppose that the point x0, y0 is 1, 2. And so then my initial condition is y of 1 is equal to 2 and still the same ODE. And I'm going to try to solve this problem graphically if I can. So I already drew here a set of axes. And now let's try to figure out what we can do. So first of all, what have we got here? So if the curve, let's say in this case, passes through the point 1, 2, right? So the initial point on the curve is 1, 2. So there's 1, 2 here. It's maybe somewhere, let's say here. If this is my point 1, 2, so what do I know? I know that y prime at 1, 2 must be y over x. So this is 2 over 1, 2. So the slope at the initial point is 2. So that means that my initial graph will have, let me see, let me actually modify this because it doesn't look like 1, 2. Actually, let me do it like this, 1, 2, so it would be the point up here. So initial slope is equal to 2, so that means that the tangent line to my curve that goes through from 1, 2 will have a slope 2. So it's roughly speaking something like that, right? So if I know the tangent line, slope of a tangent line, I can approximate my curve by a tangent line near the point. So near the point, then I can reconstruct immediately a piece of a solution curve just by knowing the point and the slope. Okay, so but then what do I do with the rest of the curve? Can I reconstruct more of it and not just a single small piece? Well, let's just play some random game for a moment. So let's say I want to find the slope at a point maybe 1, 1. So what's the slope at 1, 1? It's according to this expression, slope at 1, 1 is going to be 1 over 1, which is 1. What is the slope at 2, 2? That is 2 over 2, so that is equal to 1 again. Well, but then what can we see here? If I want to find now all points, so I want to find all points on the plane, where the slope is equal to 1. So where would those points be? Well, the slope is equal to y over x. So y over x has to be equal to 1. And that means that y must be equal to x. Okay, can I find all points where the slope is equal to 2? Let's see. Let me paste this here. Well, so then it's the same problem, right? So all points where the slope is equal to 2. Or what should happen? I would want then y over x, right? Because the slope at the point xy is y over x. I want to find all points where y over x is equal to 2. But if y over x is equal to 2, then y must be equal to 2x. Okay, so what does that mean? It means that as long as I look at the curve y equal to x, which is a straight line through the origin. So anywhere on a straight line at 45 degrees through the origin, I would expect that the slopes of the tangent lines are going to be equal to 1. So that is a line y equal to x, and we just saw that anywhere on the line y equal to x, the slope is 1. Likewise, if I look at the line y equal to 2x, so let's draw that line. Oops. That's a line actually that passes through our point here. Everywhere on that line, the slope is 2. So what can we see? We can see that everywhere on the line y equal to 2x, the slope is equal to 2. So if I start from my original point, then the slope is 2. So I move along the line a little bit up here. I measure the slope at this point. It's still equal to 2. So I can continue because I'm lying still on the line y equal to 2x. I'll have to continue moving along the same line because the slope is still 2. And so from this, you can see that y equal to 2x is actually a solution of my ODE. And so therefore, and because it passes through the point 1, 2, then that solution looks like y equal to 2x. And the same logic implies that, so y equal to x is a solution. In fact, y equal to any number, any constant times x is a solution. So the observation that we make here y equal to kx is a solution for all k. And we can test this. So if y is equal to kx, oops, then y prime is equal to k. And if I go back to my equation, y prime is equal to k, which is the same thing as kx over x. And kx is y, so this is y over x, and that's my original equation. So this checks. So once again, the graphic reconstruction of solution in this case works in the following way. Basically, what I do is at every point on the plane, I can draw a short segment of a curve that goes through that point simply by using my equation to compute the slope at that particular point. And in this case, it turns out that all points on a line, on any straight line that goes through the origin, will have exactly the same slope as that line. And so therefore, each line is a solution. And in the next lecture, we're going to look at a few more examples of this.